Hi everyone, this is Group 79 and in this video we will be walking you through the fifth and final project of CS6310 Software Architecture and Design for the semester Fall 2021. The group consists of Michael Engelbert, Sabarish Hariharan, Frank Hoffman, Kyle Rasmussen and Arne Sahe. Though all of us worked on multiple parts within the project, for simplicity we will each be presenting on one full topic. As the first part of the video presentation, we would like to demo how our program handles the requirements that were provided to us, and I, Sabarish Hariharan, will be going over this part. In this section, we'll only be covering those aspects which were not already covered during the A3 submission. The first new requirement that we had to account for was if a user tried to create two stores of the same name, it should error out indicating that the store identifier already exists. As you can see on the screen, our program does exactly that. For example, if Kroger was created twice, it executes the first command successfully, while the second time we try to create Kroger, it errors out as expected, while also letting another unique store Publix to be created. Display stores will display only the two valid stores that were created and will display them in an alphabetical order per A3 requirements. The next requirement we incorporated was for the program to throw an error if we decide to sell an item from the store that was never created, and also to ensure only unique items are being sold by each store. As expected, antipasto cannot be added to Whole Foods since the store was never created, and cheesecake cannot be added to Kroger since it was previously added. Similarly, when displaying the items that each store sells, in case the store was not already created, we will throw an error saying that the store identifier does not exist. The makePilot function is improved to prevent a new pilot from being created if the pilot ID and the pilot license were already associated with another pilot that was created before. The displayPilot function, as expected, only indicates the two valid pilots with unique pilot IDs and account as shown. The makeDrone function is altered to catch error conditions such as not letting the user to create a drone for a store that was not already created, or if the same drone ID was to be used for another drone in the same store. Similarly, for displaying the drones, we will be throwing an error back to the user if they requested to display the drones for a store that was never created. Three new error conditions were handled for fly drone functionality, where a user will neither be able to assign a drone to a store that was not created, nor can they assign a drone that was never created to a pilot. In addition to this, if the pilot identifier is not present, the drone to pilot association will not be complete. If a drone is assigned to a pilot, the display function will also have a flown by attribute with the pilot's name being displayed, as it is being shown on the screen. Similar to the makePilot function, the makeCustomer function will also throw an error if a new customer were to be created with a customer identifier that was already created. Display customers will be displaying those valid customers that were created using the commands above, and will also be displaying them in an alphabetical order. An order will not be initiated if the store does not exist in the database, or if the order identifier was already created, or if the drone ID does not exist, or if the customer ID does not exist. The program handles these errors as expected, and we can see clearly that it is being demonstrated on the screen as well. When the user wants to display the orders for a store that was never created, the application will throw an error, as we can see on the screen. Similarly, errors will be thrown in the following scenarios for request item function. When requesting an item for a store that does not exist, when the order identifier does not exist, when the item does not exist, if the same item is added again to the order, if the customer does not have enough credits, or if the drone cannot carry any more weight, and the command will be successfully executed otherwise. Now we will be displaying the current state of the system with orders belonging to each store, the customers, their credit and ratings, the revenue of each of the stores, pilots and their experience, as well as drones and the pilot associated to them if any. When the order is executed using the command purchase order, it executes successfully since it has a valid store and order ID. The expectation here is that after the execution of the order, we can clearly see these changes as shown on the screen. The output exactly matches what is expected based on the requirement document, and you could clearly see that where the credit available for the customer has changed, Kroger's revenue has increased, trips left for the drone has been made to 0, the pilot experience has increased by 1, and everything else remains constant. The purchase order command will error out in the following scenarios where the store identifier does not exist, or when the order does not exist, or when the drone needs to fuel, or when the drone does not have an assigned pilot. We will now be assigning drone 2 of Kroger to FFIG8 or Phineas Fig the pilot, and then be completing purchase D order ID. Below, we can clearly see that customer Carlos Cherry's credit has decreased while the revenue of Kroger has gone up. And we can also see that the drone ID number 2 strips has decreased and points out that Phineas Fig is assigned as the pilot and the experience of Phineas Fig also goes up by 1 while everything else remains unchanged. Similarly, we will execute purchase A order for Publix and showcase that the program meets the requirements per below. The customer credit has reduced while the store's revenue has increased. Drone 1 of Publix has the number of trips reduced by 1 while the pilot Jillian Grapes experience has increased. For cancel orders, we will be throwing an error if the store or the order does not exist. If we cancel a valid order for a particular store, it will be deleted from our order list as shown on the screen. We can clearly see that the display orders function of Kroger returns no pending order and the customer's credit, Kroger's revenue, the drone statistics and the remaining parameters stay unchanged as expected. Finally, we can see that upon executing the stop command, our program terminates with the expected output. Now, I will be turning over the presentation to our teammate Frank, who will be going over first of the 3 ADRs, performance.
I'll be talking about performance. For performance, what we decided to do was multi-thread the application. To do so, we broke it into a Java server component and a Python client component. The Python client will either take a file input or just take input from the command line. It will open up a port to the server, send a message, receive a message, display the result, and then wait for more input from the user or from a file. The server application is basically main, which calls a request handler service and a stop service. The request handler service will create a server socket, and it will listen for requests. It will also create a thread pool, and when it accepts a request, it will send it to the thread pool for execution. The thread will contact the server and send the client back a message, and then go back into the thread pool. Because threads are handling this that aren't the actual server itself, we implemented something special to get stop to work properly. The stop service is listening on its own socket. When it receives a message, it will signal the request handler service using an atomic boolean to stop whenever it gets the next message. To ensure that it does get the next message, the Python client will also send a message to the request handler service after it sends one to the stop service. Then the request handler service will close its own socket and kill the thread pool and return. Stop service will also return. Both will join, and then the system will exit. We've made some changes to the query code to account for the extra performance. For instance, for fly drone, we lock the drone when we wish to make changes. That way, pilots can't be set on multiple drones. When requesting item, we lock the customer and the drone, so that way the credit and the drone order weight does not change. And when we purchase the order, we lock the drone for subtracting fuel. And now I'll talk about our demonstration. So for our demonstration, we have 3 order flows. Each flow will create a small set of stores. The pilots, drones, customers, items, starting the orders, adding items to the orders, and purchasing the orders. And we're going to time the difference between 1 order flow running and 3 order flows running at the same time. This is the first order flow. You can see orders are coming in. All right, and you can see that it took 9.4 seconds. We are going to restart the server and clear out the database. And while we do this, I'll add another caveat. Each item, there will be 40 orders assigned by 1 customer to 1 drone. Each order costs 1 credit and has 1 fuel, which will be relevant shortly. Starting the server again. Has to reinitialize. There we go. And now we're running all 3. See the orders coming in. All right. And 9.8 seconds, slightly slower, but many more requests were serviced. Now we can go to a different Python client. we'll display stores. You'll notice that each store, which has been assigned 40 orders, each order costing $1, now has $1,040 in revenue, where they were initialized at $1. You'll notice that certain pilots who have been assigned have 140 experience instead of the default 100. You'll notice that the assigned drone has both a pilot and 40 less trips. And you'll notice that the ordering customer has 40 less dollars or credits than everyone else. And that is our demonstration.
All right, so for the robustness portion of this assignment, we decided to implement a database that is hosted on Docker. The purpose of this database is to be able to store data while the program is running in case the program crashes and we need to retrieve the data from the database to restore the last save state of the program. So let's go ahead and get the database up and running. All right, and as we can see, it is up and running on Docker. So let's go ahead and get it running on SQL Workbench. All right, looks good. And as we can see, we should have an empty database. Yep, looks good. Okay, and then we can start writing commands to it. Actually, we need to connect the client to the database first. It looks like it's connected. So we should be able to write commands, make a store. All right, we should have a store here. Yep. And let's make an item. All right, we should have an item, and we have an item in the database. All right, and let's go ahead and see what happens when we lose connection. All right, so the client should have lost connection to the database. And we can see we no longer can write commands to the database. So let's reconnect and see what happens. All right, so the program is back up and running after it crashed, and we should be able to start writing commands to it again at the same save state that it was at before. All right, and let's continue to add a few more things in here. Okay. All right, and so we should have some more items. Let's see, a pilot, drone, delivery service. All right, everything looks good. So let's go ahead and make an order. All right, order is made. So the way we make sure that the database does not corrupt data or commit data that has not been safely transferred is by wrapping queries into database transactions. And this allows us to make sure that if the server crashes in the middle of a transaction or query, that the database is not updated into a wrong state. And if the database does crash while the transaction is open, we will roll back the database server to a safe state. So let's go ahead and see this in action. We should have some time. Cannot find simple. Okay, built successfully. So what we're going to do here is reconnect to the database. And what we're going to do is we are going to open an order transaction. And while the order transaction is open, we are going to kill the connection to the database. And once that connection is killed to the database, the transaction is expected to roll back the database state. And we should see this here. So let's go ahead and create a new order. And we should see a new connection pop up as soon as we run this. All right. As we can see, we got a new connection here. Let's go ahead and kill it. Kill the connection. Let's see what happens. All right, and as we can see here, the transaction was rolled back because the connection was killed during the transaction before it was committed to the database. So this provides us a robust database in order to ensure that no data in the database is committed without breaking any rules. And yep, that's how it works.
My name's Arnesh, and I'll be covering archivability. For archivability, what we set out to accomplish was that using a command through the terminal, the user could clean up or archive any data older than 3 months. So for the purpose of this demo, what I'll be doing is I'll be creating some stores, items, and some order information, and we'll run the cleanup command afterwards, and we'll be able to see that the data is purged from the database. So if we go to display orders for a certain store, we won't see that data. And what we'll also see is a CSV file containing all of that data that we exported in an archive file with a corresponding timestamp. So let's get started. First thing I'll do is I'll just copy the commands from the A4 document that creates some items, some orders, and any associated data for customers or pilots. And I'll just go ahead and paste that into our terminal here. So this will take a second or two to run. Okay, so just for illustration purposes, we can do display orders for Kroger. Looks like it got appended to display pilot. So if we just do display orders for Kroger again, we can see that we have our purchase A, purchase B, purchase D, and we have the associated items for those orders. And if we go to display orders for Publix, we'll see purchase A here as well with that cheesecake item. So now what we'll do is we'll go ahead and run that cleanup command, and we'll get a message saying that the data has been archived. So now what we'll actually do is we'll go to the project folder, and we'll look at DB data. There's a folder called delivery service, and in there there's a CSV file with the current timestamp in UTC time, so it's showing 7 a.m. of the following day, December 7th, and 6 a.m. And if we go ahead and open this with Excel, we'll be able to see the order date as well as the order ID, store name that these orders were associated with, and then any assignment information for pilots and drones at the time of the cleanup command was run, as well as some items and their quantities and prices for those orders. From here, we can go back to the terminal and take a look at the orders for Kroger, and as expected, we don't see any items or any orders associated with Kroger. And if we go ahead and do the same thing for Publix, likewise, we just don't see any orders there since they've been cleaned up. All right, thank you.
Moving into a quick description of our diagrams, starting with our class model diagram, you can see here that we've modeled each of our classes, including the delivery manager class, which creates instances of other classes, as well as connections to our database server. Next, we have a deployment diagram, which shows how our system was set up as far as the Docker host, the MySQL server, our applications, and the connections between them. Next, we have a database diagram. This diagram shows the separate tables in our database schema, with primary keys underlined and foreign key relationships represented by these arrows. Next, we have a sequence diagram illustrating robustness. Essentially, what's being shown here is that when a power outage occurs, a rollback happens and the transaction is not completed and no information is sent to the SQL server and this database does not change. Next, we have a sequence diagram for archivability. This essentially is showing that a store employee will provide a request, creating a CSV file of data older than a certain date and removing that data from the orders table in the database. Our sequence diagram for performance is here to show that multiple users can use the system concurrently, and the system will create separate threads to allow them to do so. Our use case diagram shows two different user types: the customer, who creates orders which are stored in the database, and then the delivery service manager, who can kick off an archive order data transaction or function, which will remove data from the database and additionally export that data into a CSV file. For robustness, we also created a communication diagram. This illustrates similar features to the sequence diagram, essentially showing that for the thread where the power outage occurs, no information is sent to the database and the transaction is rolled back. And we have a performance diagram showing that two threads can run concurrently for two separate users, returning separate data. Okay.